Hello, year 11. So last Friday we did this practical, people who were in. So there was quite a lot of people off, and you'll need to read through this. This is page 226 in your notes. The method is all there. It is one of the prescribed practicals, so it is one that you need to know. And really it's just sort of proving the principle of moments. So if you remember the principle of moments, if an object is in equilibrium, the sum of the clockwise moments about a point is equal to the sum of the anti-clockwise moments about that same point. So we just had like a fixed mass on one side, did we? Flip, I can't even remember how we did it. And we moved the other one around and measured the distance that made it balance. And then calculated the moment on both sides, just to show that they were the same whenever the meter stick was balanced, or roughly the same. We probably didn't get perfect results. Okay. Now, at the end of the lesson then, oh look, there's the principle of moments there. So at the end of the lesson, I very quickly showed you another couple of practicals. So we're going to spend time now going through those, talking about them properly and filling in our notes. One thing that I hadn't actually said to you was that with the principle of moments, something is balanced, and that means everything's in equilibrium. So the clockwise moments are equal to the anti-clockwise moments. But remember from Newton's first law, if something's in equilibrium, it means there's no resultant force. So that means any forces that are acting up the way must be equal to any forces that are going down the way. And that ends up coming in sneakily handy sometimes in calculations. So we just need to make sure we remember that. Anyway, back to these practicals. So there is a practical that we did to find an unknown mass. So the proper method is here. I'm just going to talk you through what we did, and I remembered to bring home the numbers that we got in our whenever we did it. I did not remember to bring home the numbers for the next one, so we'll have to make those up. So if you were to use the principle of moments to find an unknown mass, then you would set up a lever. So we used our meter stick and pivot it at the center. So remember, with a meter stick, to pivot it at the center, that's just going to be the 50 centimeter mark. Then we hung an unknown object, so we used a stapler. So there's my stapler hanging down from the meter stick. And then we hung a known mass from this other side. So we used 3 newtons. Okay. Now, we hung the 3 newtons 25 centimeters from the pivot, and then we moved this around until the meter stick balanced. And then that means we'll be able to measure this distance here, and we know that because this is balanced, the moment that's created by this 3 newton weight, by doing the force multiplied by the distance, must be the same as the moment that is being produced by the stapler. So we'll have measured the distance, then that means we can get the weight or the force, and from that we'll be able to calculate the mass. Okay, so that is our setup. I think that's everything we need to put in our setup. Let's turn over and fill in the calculations. Right, okay, so for the calculations we've got, you're going to kill me, but I want you to sketch this out again just so we have it handy. So we had 3 newtons acting down the way, and that was 25 centimeters. And we had our stapler hanging here, and we measured this distance that made it balance. So we measured the distance, and that was 36.7 centimeters. So whenever this stapler was hanging from the meter rule, 36.7 centimeters from the pivot, it made the meter rule balance with this 3 newtons, the 25 centimeters from the pivot. Okay, so that means we can use the fact that anti-clockwise moments are equal to clockwise moments. And we know this statement here because of the principle of moments, because the meter stick is balanced. We know the moments, anti-clockwise and clockwise, have to be equal to each other. So to calculate the anti-clockwise moment, if we look back at this, this one is making it turn anti-clockwise. Isn't it? Yep, this one is making it turn clockwise. And the force, I forgot to mark it on there, the force acting down there is just the weight of the stapler. So for the anti-clockwise moments, write in like the bit of the equation that you're using, it's force times distance. Clockwise moments for this, force times distance. So for our anti-clockwise, the force is the weight that we're looking for, multiplied by the distance that we measured to make this balance, and that was 36.7. And then for the clockwise, this is our force, it was 3, and the distance was 25. So 36.7 W is equal, oh look, first of many mistakes, that was 25, sorry, equals 75. So then to get W, we just have to divide 75 by 36.7. Okay, that gets me 2.04 newtons. So that is our calculated weight of the object, 2.04 newtons. To get the mass, we use our W equals mg equation. So that means mass is weight divided by gravity. The weight is 2.04, gravity is 10. So that gets 0.204 kilograms, which is 204 grams. So that's what we got by our moments calculation, 204 grams. Now, then, and people will, I'm not lying, we did get really good results. We set our stapler on the balance and we measured the mass and it was 203.2 grams. That is pretty darn close, isn't it? So it is a good experiment. It does generally give good results. So there we go. We need to know that one. The next one that we need to know is the practical to find the mass of a meter stick. Now, we need to make use of the fact that we know the weight of a meter stick all acts through its centre of gravity. So the way we would do this one would be to take our meter stick and pivot it somewhere that isn't at its centre. So say we pivoted this at the 20 centimetre mark, right? I'll just mark that on so I don't forget that I've said that. So if we have this meter stick pivoted at the 20 centimetre mark, we know that its weight acts at the 50 centimetre mark. We know the weight acts at the centre of gravity because a meter stick is uniform, so the centre of gravity is at the centre. So that means this weight is acting 30 centimetres from the pivot. Okay, hopefully we're all right with that. Now if I was just to set this down like this, then obviously it's not going to stay balanced, it's just going to tip that way because we've got a clockwise moment produced by the weight. So all we would do in this experiment is take a weight and hang it from this side so that it's creating an anti-clockwise moment. So say that we used 2 newtons for this and we hung it 10 centimetres from the pivot. So this is the one I did not bring our results home for, so I am making these numbers up. But let's say that was the case. So if we took a meter stick, we pivoted it at the 20 centimetre mark and we hung 2 newtons 10 centimetres from the pivot. Then doing that, let's say that made this balance. Okay, so if this is balanced, then we'll be able to use our anti-clockwise moments equal clockwise moments. Right, we need to actually write down our method. So set up a meter row, fill this in, pivoted at the 20 centimetre mark. Hang 2 newtons from the meter rule on the left hand side of the pivot. Move the 2 Newton weight along the meter rule until it causes the meter rule to balance. Measure the distance of the 2 Newton weight from the pivot. Oh my goodness, I'm not even on the screen anymore. There we go. So we said up here that in this imaginary situation where our 2 Newton, say it was 10 centimeters from the pivot, whenever that caused it to balance, well then we can do the calculations to figure out what weight this imaginary meter stick would be. Which I'm probably going to have to go over the other page, yeah. So I'm going to have to redraw this. You're going to have to redraw it too. So we have our meter stick. We've got our 2 newtons, and that is 10 centimeters from the pivot. And we had the weight of the meter stick itself, and that was 30, wasn't it? Yep. So, anti-clockwise moments are equal to clockwise moments because we have moved this around to make it balance. This is anti-clockwise, and this one's making it turn clockwise. So, force times distance equals force times distance. So for our anti-clockwise, our force was 2, and we said that that had to be 10 centimeters from the pivot to make it balance. For clockwise, the force is just the weight of the meter rule, and that was 30 centimeters. So 20 equals 30 W, that's going to be 0.67 newtons. It's a very, very heavy meter rule. Oh, it's a very light meter rule. Okay, once we get the weight, we can use that to calculate the mass. So 0.67 over 10 is 0.067 kilograms, which is 67 grams. And then we didn't actually measure the real mass. Real meter rules are about 100 grams, so that I didn't pick the best numbers. Okay, hopefully that made sense. I felt like it was a little bit all over the place there, year 11. I do apologise. So fill those in. Make sure you understand what on earth is going on. And I think that might do us for today. And then tomorrow we'll do some calculations. It's a bit short, isn't it? Unlucky, we're going to do some calculations today. Sorry guys. Right. Okay, so this are very similar to the calculations we have just been doing there in those practicals. So, calculate the distance for the lever to balance. So if we have something like this with these different weights sitting here and different distances from the pivot, this is how we need to always set our working out for this, okay? Always, 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 always. So if it's balanced, we know anti-clockwise moments are equal to clockwise moments. Okay, so force times distance equals force times distance. So this one is making it turn anti-clockwise, and this one is making it turn clockwise. Remember the two different ways that you can check that. Put one finger in the pivot, one on the force, and follow it around and see what way it's going. So this one's anti-clockwise. Or the other way is you can put your pen on it and push this end down in the direction of the force and see what way that's making your pen turn, and it's making that one turn clockwise. Okay, filling in our numbers. So force 125 and the distance from the pivot is 0.8. This one, the force is 200 and we don't know what distance it is from the pivot. So 125 multiplied by 0.8 gives me 100. And then divide both sides of your equation by 200 and you'll end up getting D is 0.5 meters. Okay, now the wee note down at the bottom of the page here is just saying that it's definitely easiest logically to set your working out like this. See the way, now I haven't done a perfect job of it, but if I have my equal sign lined up underneath the pivot, then my anti-clockwise are lining up with my clockwise, and then you know you're always picking out the information like from straight up above. Now, things that we need to be careful of. Questions won't always give you this distance from the pivot. Sometimes they'll give you the distance from the end and you have to figure it out. And look out for if a force is acting up the way, because then it won't match up with your working out underneath here, like directly underneath. So my advice is to keep marking on each force, whether that makes it turn clockwise or anti-clockwise. Okay, another example. So a boy weighing 600 newtons, here he is, sits 1 meter away from the pivot on a seesaw as shown here. What force 1.5 meters from the pivot is needed to balance? And then find the size of the upward reaction force exerted by the pivot. So let's look at part A first of all. So if it's balanced, we know that anti-clockwise moments are equal to clockwise moments. Okay, so for the anti-clockwise we've got our force times distance, and for our clockwise we've got force times distance. So anti-clockwise force is 600. The distance it is to the pivot is 1 meter. And clockwise is this unknown force F, and it's 1.5 from the pivot. So 600 equals 1.5 F. So F is going to be 400 newtons. Let me check that. I do not trust my mental maths. Yeah, 400 newtons. Okay, hopefully you're following along with this all right. Now B is making use of that wee rule that was written down underneath the principle of moments. So find the size of the upward force the upward reaction force exerted by the pivot. Now because our diagram isn't on the screen, I'm just going to do a little sketch. So we have our pivot here. We had our 600 newtons acting down here, and we've just figured out that we have 400 newtons acting down here. And then there's this reaction force. Anytime things are in contact with each other, there'll be this normal reaction force. So we can use the fact that if this thing is balanced, it's sitting still, that means the forces acting on it must be balanced. So that's really Newton's first law, if you remember back to it. Of course we can all rhyme it off, can't we? So that means that the upward forces, so forces up must be equal to the forces down. So forces up is that reaction, and the forces down, we've got 600 plus 400. So we've got 1000 newtons there. Okay. Now, I will write on the post what questions I want you to do today, but really I'll tell you here as well. Page 233 and 234. I'll not get you to do the 235 yet. We'll do that. What day is it today? Wednesday. We'll do the rest of those on Thursday. Okay? Right, I think this was very, very random, or not very rambly, year 11. I can only apologise. I promise the standard of my videos should be better from now on. Okay? I will see you on Thursday. Goodbye.